CS203, and sorry for the delay because of the technical issue, but at least one thing I know is that this classroom has very good system of play stereo. So that's really good thing, so we'll play a lot of music and pay attention to those music that play. Sometimes they are related to the course that we are teaching. So, the reason why I always like to start with this course is that why are we taking CS203, right? So, if you have already submitted a course agreement, I bet you already answered this question. So here's the word cloud of your answer. So apparently, if you look at the answer, some of you saying that you are interested. Seriously, right? I guess you're probably to make me happy, or maybe that's true, right? But most of you, I think you're honest in a way that, I see some words like requirement, core courses, right? And requirements, right? The plural of requirement. So I know a lot of you take this course just because it's required, right? And this is what you are really interested in. So you are really interested in machine learning, you are interested in being a software developer, you are interested in artificial intelligence, you may be interested in security. And a lot of you might not think, well, this is relevant to me. And in fact, your answers are pretty consistent with Bard or ChatGPT with that. Right? So if you check like the answer from ChatGPT or Bard, right? They will tell you artificial intelligence, ML, data science, cloud computing, cybersecurity. There are both blockchain, human-computer interaction, software development, computer vision, quantum computing. They are both hot topics, right? And the reason why I pull out both Bard and ChatGPT because earlier this year I was at Google, working at Google, and that was the time that the ChatGPT just rolled out, and the whole company, including me, we are excited about the Bard. And I still think Bard has a better answer. Well, because Google donated a lot in my life, so definitely being a YouTuber, you have to be loyal to your to contribute to your life, right? So, but anyway, so your answer is pretty much consistent with ChatGPT, Bard, or so to be honest, like as a computer scientist, right? What do you care, right? So when we're saying about like developing software, you think about algorithm data structure, you think about software engineering, you thought about, okay, can I incorporate AI and ML? Can I write my code in a way that uses a fancier programming language? Can I design a user interface fancier? But in terms of computer architecture, right? I bet this is what you feel. Alright, so that's your feeling, right? So what computer architecture really is. So if you look up from the dictionary, it will tell you it's the manner in which the components of a computer or computer systems are organized and integrated. So being honest to you, we are not the ones that doing AI, doing a lot of presentations. However, computer architects like me, we are actually the hidden figures behind the success of many other areas. And again, if you ask both ChatGPT and Bard, how important is computer architecture? You are going to get very promising answers like this, right? Understanding hardware, optimizing performance, designing efficient software, parallel computer, those stuff, computer architecture affects. So even though you think I'm just a software developer, and computer architecture really matters to you because it will allow you to write more efficient code. So first of all, it won't allow you to be a fast coder, but you will, with the knowledge of computer architecture, your code will run faster. And in fact, why am I saying this is a hidden figure? So how many of you know this guy? The father of deep neural networks. What's his name?
George or Jeffrey.
Jeff. Okay, Jeffrey Hinton. Right. So listen to what he mentioned.
I think a lot of the credit for deep learning really goes to the people who collected the big databases, like Fei Li, and the people who made the computers go fast, like David Patterson and others.
Okay, so Jeffrey Hinton, he is the father, well, you said, right? You said, I didn't say that, right? You said he is the father of deep neural networks. And this is actually the talk he gave in 2017 for his ACM Turing Award. And I was there in person. And he mentioned this. I was super excited because he is really good in a way that he remembered the hidden figures behind the success of neural networks. So I'm old enough to tell you the story. So when I am an undergrad student, everyone is telling me neural networks doesn't have a future because it's not able to run on modern computers. However, computer architects like us, we really make a computer faster to make it happen. And do you remember the name he mentioned who made the computer faster? David Patterson, right? So where can you find David Patterson? If you check carefully, it's actually on the textbook that we are assigning you for this course, right? So in fact, computer architecture enables deep learning. And do you want to make a guess where David Patterson is right now? At Google. Yeah. Do you know who? Do you know where is John Hennessy? Well, he is at Alphabet, a label up than Google, right? So a lot of you might think, okay, if I want to attend Google, right, computer architecture has nothing related to me. But think about the chair of Alphabet is John Hennessy, and he is a computer architect. David Patterson is in Google, right? So computer architecture is actually very important. And in fact, when I work at Google, we have 4 buildings in my site, and in Sunnyvale, and everyone is working on something related to computer architecture. So computer architecture is indeed important for all of us, right? So right now, I know you have been sitting around for maybe 20 minutes, 20 minutes, 10 minutes? Oh, 10 minutes, right? So I want you to have some exercise. So if possible, can everyone stand up? And right now, you can stand on, okay, so we have 2 sides, right? So I am going to ask you a few questions, right? So let's split here in half. If you think this question, the answer to this question is correct on my right-hand side, if you think it's incorrect on my left-hand side. Go, 30 seconds. Run. Okay, let me put my timer up. Just pick. Have you ever watched this kind of game show before? Okay, 30 seconds. I should have a timer. 30 seconds, 30 seconds. Okay, 30 seconds, 30 seconds. So you guys are on the right, on this side? Incorrect? Who is on the left-hand side? Okay, we need a border. Give people some space, right? They need to be on the stage, right? Okay, so the answer to this question is yes. Okay, so for those of you who vote no, I know you have a reason you want to vote no because you want to have a seat earlier. So welcome. Go back and have a seat. No. Those who pick incorrect have a seat. All right. Let's see who will survive. Okay. Second question. Moore's law is currently slowing and discontinuing. Right on the left-hand side. Incorrect. Wrong on the right-hand side. Okay, 15 seconds. Anyone want to move? Last few seconds. Okay, someone move on the right-hand side. Are we all good? Okay, so for people on my right-hand side, which is your left-hand side, you can have a seat. Okay, so, well, we only have a few now, right? So if you are still standing, come here. Do you feel like you are in a game show right now? I hope we have camera so that we can capture everyone. Right, so this is the left-hand side. Well, this is the, okay. Okay. Okay, next question. Are you guys ready? Are you guys ready?
Yeah.
Okay. Programs with lower computational complexities are more efficient. Anyone want to change? 20 seconds. Isn't this fun? Should we do it every class?
This should be our exam.
Should be on exam, right? Because right now you see a lot of people fail before you, right? And this is in serial. Only the ones survive at the last can pass, right? Okay.
That would be really sad if you all the other
Okay.
except for-
Last 2, 1. Okay. Okay, here we go. So the answer is no. All right, you can have a sit if you want. Okay. So next question. Program performance scale with its main computational complexity. Okay, last 10 seconds. Anyone want to change his mind or her mind or their mind? Okay, the answer is no. All right. Are you ready for the next question? The next question, algorithm complexity is less important if we have unlimited parallelism. Okay, so people are start choosing those counterintuitive ones.
Is it like time complexity space?
What?
Is it like
Yeah, time complexity. Okay, so looks like yes. All right, next question. Memory operations are more important for large matrix multiplications on modern computers. 30 seconds. Okay, no one want to move? Okay, the answer is right. Okay, next question. Efficient programs should leverage more bitwise operations. No one want to move? Are you sure? You guys are sure? Are you sure? Okay, the answer is no. All right, everyone go back. Actually, I have some more. Right, but you know, as long as the good news for me is that as long as no one passed the whole set of questions, I still have something to teach you throughout the quarter, right? So okay, so now you know why CS203 because a lot of cases we saw our computers work in this way, but you know, as this right yes or no question, you answer. You start to feel that, my programs are probably running in a way that I was thinking about, right? So that's why you need to take CS203, right? A lot of people who taught you computational complexity, throughout this quarter, I will tell you how wrong they are. All right, so so the reason why we want to take CS203, right? A lot of you probably played this game before, and I'm a big fan of this, right? So if you ever watch the animation, you know there's always a section like this, right? We give you something like this, and want you to guess what is that, right? So most of the time, without sufficient knowledge about computers, you may imagine your computer is something powerful like this, right? But end up, what you actually have is this, right? Look at the tail, right? Did you see that tail? Right? This is exactly what it is, right? But you thought I have a computer as powerful as Pikachu, so I try to ask Pokemon to do all the electro type attack. But that's not going to work, and you start to plan your croquet home, right? So if you have a computer, you don't use it in the right way, even though you spend thousands of dollars on it, you're not going to exploit its full power. So another thing, right, what I like to say is, okay, a lot of people, well, you are good kids, right? And one day you earn a lot of money, you probably buy this watch list for your family, but you know, there is a panel like this, it's very complicated, and if you don't know how to use it, it's a waste of money. Or, you know, sometimes you want to give the best car to your parents, you think it has auto-piloting, it will help your parents better, but turns out, what if they don't even know how to use the touch screen? Right? So it's pretty much like this. So without the knowledge of computer architecture, you are pretty much writing programs or use your computer in a way that like you don't know how to use the panel of Tesla. Is that good? That's definitely not good, right? So that's why we need to care computer architecture. So some of you are thinking about, okay, are these answers right? Right? So let me show you something, right? So most of the modern general purpose computers, they all have processors and memories. So here are some evidences. Well, first of all, right, you have the knowledge like this. So throughout our polls, the survey, a lot of you already filled this in. So you know, like processor memories, they are a big part of our computers, right? And the reason why we have processor and memory everywhere is because every modern computer, every modern general purpose computer, I want to say again, every modern general purpose computer is an implementation of the von Neumann architecture. So what's von Neumann architecture? Anyone remember that? Anyone recall that? What's von Neumann architecture?
Contains 5 parts.
5 parts? Like
Memory.
memory? What's the second one?
Processor.
Processor?
ALU.
ALU is part of the processor, right? What else?
Input, output.
Input, output, what else? Storage. Okay, so, okay, you got some of it. Von Neumann architecture isn't that complicated. So the idea was this guy is Jean von Neumann. I bet you will see this guy again and again this quarter. So, von Neumann architecture is this. First of all, your computer is composed of 3 main parts: processor, memory, and well, in the very beginning, there is nothing called storage in von Neumann architecture. But right now, because you want data to be persistent, so we always have the storage associated with the computer. So these are the 3 main parts of von Neumann architecture. So how are we operating this von Neumann architecture is, first of all, once you have a program, it will exist on the persistent storage, and each program is supposed to contain 2 parts: the instructions and the data. And the instructions are the commands that you want the program to do, and the data are the elements that the program can work on. So if you want to execute a program, what you need to do is that you have to load the program that you want to run into the system's memory. So that's why memory is essential. So everything has to present it in memory, to be presented in the memory before we can run it. Everything has to be in the memory first. And then what happens afterwards is that your processor will fetch an instruction by their execution order from the system's memory. And what happens after is that the processor look into the content of that instruction and decide what to do. So if it's an ALU operation, like you said, it will invoke the ALU inside the processor. And if it's an instruction that wants us to access data, that's the time the processor would access the data memory. And once the processor is done with one instruction, it will advance to the next instruction in the program. So that's the von Neumann architecture. So you might want to ask, what's the good thing about this architecture? You think this thing is very natural. However, why this becomes the dominant architecture in the world is because imagine that. If today I load a completely different program into the computer can perform a completely different function, right? One example, you must experience that, right? When you are a kid, right? You ask your parents or your family saying that, okay, I need a computer to assist my learning. Of course, in the daytime, you use the Word or some other software that is the productive software, right? But after they sleep, tell me what you do, right? LOL? What else? Something like that, right? So, but how does that work, right? The same computer, it could be a working machine, but also an entertaining machine, because the von Neumann architecture allows that. Because the von Neumann architecture allows the computer to completely performing different, because if we load different content into the memory. So that's the beauty of von Neumann architecture. So without von Neumann architecture, you can imagine every computer is like a good old day arcade machine. How many of you played those arcade machines before? Okay, right? So what's the difference between arcade machine and general purpose computer?
Arcade machine runs one program at one time.
Right, it can only run one program, right? So if it's a slot machine, I was afraid that you are saying that, okay, it has a slot. It's a bar that you can pull, right? So if you go to Las Vegas, every slot machine, they can only do slot machine. And in fact, if you check, if you tear it down, those slot machine nowadays, they also have a PC inside. Some of them even run Windows. So I'm not kidding, right? So if you go to Las Vegas, you can try that. I'm sure the cops will catch you, right? Or the bodyguard, right? Las Vegas bodyguard. Can you imagine that? All right. So to give you some evidence about what a real computer looks like, so let me show you a few photos. And first of all, I can show you a desktop computer. So this is actually from a desktop computer that I have. Right, so let me show you this. Then give me some time. Let me put everything together first. Okay, I guess that's probably it. So most of the time, if you take the case out, this is what you will see as a computer, right? So first of all, right, you remove this. This is where you can plug in your monitor, right? So this is a GPU card, and you will see a heatsink with and under the heatsink is a processor. So here's the heatsink. If you're interested, you can pass it around. And a lot of you probably never see a processor, right? The processor is actually right installed in this socket. And if you take the socket out, you can see this is the back of the processor. And it has this kind of soldering place to allow the pins on the motherboard to communicate with the motherboard. All right, pass it around and be careful. It's worth $100 at least, even though it's outdated. So a lot of you were asking about where's the memory, right? The memory is right here. So this is a memory module. This is a DDR4 memory module. You can never seen it, pass it around. And a lot of you saying that, okay, I do a lot of machine learning. I'm curious about what a GPU looks like. And well, so this is a grandfather of GPU and it's for gaming. But in terms of the structure, is nothing too different from the high-end GPU you will see. So first of all, it's made as an expansion card, and even with the high-end GPUs, they still go through the PCIe protocol these days. So here are the metal pins they connect with your motherboard. And through the motherboard, they can talk to CPUs and your memory. And because GPUs, they are typically very hot, So you can see they have an even larger heat sink than the processor. And under the heat sink, here is the main GPU chip. So you can look over it. All right, where is my storage? So storage now has many types. So if you have a newer computer or even a laptop, you will see an NVMe SSD like this one. And here is the socket of an NVMe SSD. And if you have a grandfather old computer, you probably would have a cable connecting to a solid state drive like this. Okay. And here's the motherboard. So everything will be put on the motherboard. So that's what a desktop computer looks like. So it has processor, it has DRAM, and it has storage, right? So that's an example. You see processor, DRAM, and storage. Okay, some of you say that I'm a big fan of Chromebook, right? So although I'm using a Mac, and to be honest, when I'm at Google, I'm also using a Mac. But some of my colleagues, they are big fans of Chromebook, and they say, well, I only need a server computer. But what a server is indeed just a computer with a motherboard with multiple processor sockets, even more DRAM sockets, and still you need space for peripheral and storage. And MacBook, right? This is my MacBook. If you tear it down, you will see there is a single chip with processor plus GPU and some solid DRAM chips on the motherboard. So that's why some people hate Mac, because you cannot replace those DRAMs that is solid. And you also have the solid state drive as the storage, and Wi-Fi modules and codecs. All right, how many of you got this already? Oh, you did also. All right, I also have one, but I haven't started using it because my bumper is still on the way, right? And I already see a lot of reports saying that you should have a bumper, right? So, okay, this is you will see it next Tuesday. So next Tuesday, this is what you are going to see. This is my iPhone 15 Pro, right? And if you tear it down, this is what you will see. You will see a single chip with processor plus GPU and die-stacked DRAM. And they also have NAND flash as the data storage. And again, this is a phone. So a giant part of the motherboard has network modules and codecs. They are from either Qualcomm, Broadcom. Some of them are made by Apple directly. And there's also ultra-wideband chips and also sensors trying to sense how fast you are, how hot you are, temperature. And also power management ICs, right? Okay, so for gaming console, right, PlayStation 5. Well, there's also processors plus GPU and DRAM. Okay, different shape, but still DRAM. Okay, and peripheral solid-state drives, right? So Nintendo Switch, again, processor plus GPU and DRAM and solid-state drives and network modules, right? So everyone looks the same. Okay, even Tesla, that's a different enough computer, right? So this is the motherboard of Tesla. I mean, the motherboard controls the car, not the motherboard behind the monitor. So it still have two processors, and the reason why they need two processors is not because they want it to be faster. Remember, it's a car, so they want redundancy, right? And they also have two sets of DRAM and a lot of power management IC and two sets of storage, right? So that even the car is nowadays a small computer, right? So processor memories are everywhere in our computer. And the reason why we want processor and memory are everywhere is just because they are all von Neumann computers. And these are essential for all von Neumann computers. So do you guys all agree that processor and memory, they are essential for every computer? Yes, right? So that's why that question is correct. And now, a lot of you might say, well, it looks like the program is instructions, are in a set of instructions. But most of the time, I don't write my program in that way, right? So how does my C program, or in general, program code becomes a program, right? So first of all, you have a source code, and you press a button, it triggers a compiler, and the compiler would generate the binary like we said, with instructions and data. And then when you need to run the program, if you have dynamic linked library, that's the time the operating system or the linker inside your operating system would combine your code with those linking library and put them all together into the memory. So now in your memory, you would have part of the instructions from here, and then some of them from here, some of the data from here, some of the data from here, combine them together, put them all together as a single program, right? In a DRAM, and then your processor start running it. So this is a real content that I use a program called object dump. And as you can see, each of the programs should at least contain two sections. The text section, which contains instructions. So here, if you decode it in ASCII mode, it doesn't make any sense because they are indeed computer instructions. So if you check the content of this, they are corresponding to a certain instructions. And like C7 as an instruction, all the zeros, these are no ops. These are, so this is probably like a pop instruction as far as I recall. Right? So these are instructions and these are data, right? And some of the data are decodable. So for this one, it tells you that, well, this program is compiled using GCC on Ubuntu 2004, right? So most of the time, you don't program at this level, right? So here is some idea tells you what's happening in more technical view. So technically, if you write a C program like this with a loop, what would happen is that after the compiler will look into this source code, and they will figure out, okay, there are some of the control flow operations, and there will be some logical operations. And that's the time we are going to invoke the logical operations and control flow operations like branch instructions on your processor to change the execution flow. There will also be arithmetic operations like add1 or add that would help us to accomplish the I++ and plus equal operation. And if you need to access memory, of course, like array is large, so we won't put it completely on the registers of your processor, so they will be on the memory. So in that case, if you have memory accesses, and the compiler would generate those instructions and put those static instruction, static data, those declared already inside the data section of your program. So that's why your program typically contains these two sections, and they are both generated on at the compile time. So if you want to see a more realistic example, here is the example that I can give you. So in this class, we are going to intensively use Jupyter Notebook, and including your assignments. Are you excited? All right, can you ever imagine a computer architecture with Jupyter Notebook? So what does a real program look like? Okay, so here I have a program that is, let me see, that is matrix multiplication. So here is the matrix multiplication code. Pretty familiar with it, right? Triple level nested loop. And now if I compile it and I use object dump, here's the program that you will see, right? So first of all, you will see a lot of other sessions, but one of the session must be data. Okay, you cannot search here, which awesome, right? But here is what you will see, right? So some of them are, there are a lot of stuff that, you probably don't know what is that, right? But what I want to tell you is, okay, here we go, right? So this is the section, text section, as we mentioned. This is where you are going to start your instructions. And it tells you that, well, at the program counter 1100, here is the main function, right? Something you'll understand right now, right? So the main function is right here, and the main function contains a lot of other stuff. Like if you want to parse an argument, you probably need to use this strtol function, and there are move instructions that accesses memory. There are call instructions that try to access this, like this is vallocate, so you can probably guess this is memory allocation, right? And this is JBE. This is a branch instruction as well, right? So this is what a program really like, and at the end of the program, you are going to see like a data section. So we declare array size in this program. So the array size will be put it here. And this, and so here we have, so this is the array size. So if it's data section, ignore those instructions. What really matters is here. So you see a 0, 2 here. So you can probably guess what's the default array size here, right? It's 20 in hex. And there's comment, and here is comment section. So some of you have the, and the comment here is not the comment you wrote, or the comment for the compiler to tell you which line is not to which line. So this is pretty much what a program would look like, right? Most of the time, you don't need to program at this level, but I want you to keep in mind, no matter what program you have, at the end, you are going to see these two sections in the compiled binary. So because of your program looks like this, you can imagine what a processor would end up being is actually a collection of functional units that can perform logic operations, simple arithmetic, complex arithmetic, branch and jump, and memory operations. And there is something called instruction set architecture. Define what are the set of instructions that a processor to support. So if it's an x86 processor, the contrast saying that if this is an x86, here is a set of thousands of instructions you have to support. If this is an ARM instruction, here's the hundreds of instructions that you need to support. And it's the compiler's responsibility or the programming framework's responsibility to generate those instructions. Otherwise, no one else can really use this computer. So you can also imagine instruction set architecture in this way, right? So earlier we talked about there are two different Pokemons, right? But when you play the game, right, you don't have to do anything different. Well, you have to use these two Pokemon differently. But to control them, right, these are the 4 buttons that you need to know, right? And you know if I press B, that's probably some kind of minor attack. If you press A, that's probably the stronger attack. And if you press it longer or press B longer, right, there will be some other effects. So no matter which Pokemon, they all follow the same contract of this. Of course, because it's different Pokemon. So when they implement this A, B, the effect might be slightly different. But you can expect A is always attack, X is always, Y is always jump, something like that, right? So that's the contract. And some of you might be saying, oh, come on, professor, CS grandfather, it actually was older than my grandfather, right? So why am I using this grandfather language? I'm using stuff like Java, right? So for Java, it's still the same, right? It still have a Java C compiler. The Java C stands for Java compiler. It's not translating Java into C. Instead, what a compiler does is it translates the code into some other architecture called Java bytecode, which is Java's unique virtual machine architecture. And then Java virtual machine would dynamically translate this bytecode instructions into the real machine instructions on the fly. So some of you might experience the efficiency issue of Java. That's because it has one layer of translation, like this. And for Python, it's also similar in a way that there is an interpreter always running behind, and it parse the source code line by line and translate each line into program instructions and dynamically write those instructions to the memory for the processor to execute. Okay, so that's the basic of how computer works. And another question which I think a lot of people go back to the SID is programs with lower computational complexity are more efficient. So let me show you this demo. So for this pieces of code, I have a variable called option. So can you tell me when option is 0 or when option is 1, are we getting lower computational complexity? So the computational complexity of this program is lower when option is 0 or 1. Well, make the option 0 that the program lower computational complexity, or making it 1, making it higher computational complexity. 0 or 1? 0. Why is it 0?
I guess.
You get? Okay.
If alternate one, then we will have higher complexity.
If it's 1, we have higher complexity. Why?
Because we are sorting that.
Okay, what's the best ever sorting algorithm you can think about for its computational complexity? Quick sort, what's it? What's the complexity? N log n, right? So it's n log n. How about the second part? It's order n, right? So if you don't use quick sort, the computational complexity is actually lower. So I have a program here, which I will show you the demo right now. So I have this function calculate sum, which I will call in my main program here. You guys can see it, right? Okay, so this is the code, and this is the complete program, the array sort. So I'm calling this sorting function and also this calculate sum function, right? So that's equivalent to the code that I show you. And now, make sure that I'm not cheating, so I recompile the program, and then let me try to run it. So now I first run it with the second argument as the third argument as 1. So the third argument as 1, it actually sets the option equal to 1 if you read this line, right? So it takes about 0.1 seconds to finish, 0.163 seconds to finish the program. So now I'm running it with option 0. How much time do I take? Almost 0.6, right? Like 6 times slower, right? Lower complexity is actually slower. Algorithm complexity is less important if we have unlimited parallelism. I also have another demo for you. So quick sort, as you guys said, n log n. There's another sorting algorithm which is terrible in terms of computational complexity called Platonic sort. And its computational complexity is older. So here's the Platonic sort code. And if you're interested and you can do a quick run, you will figure out its computational complexity is n log squared n, right? So on the right-hand side, it has no means to run faster on the left-hand side through the theorist's perspective. Agree? Okay, let me show you the demo. Okay, so here, okay, matrix multiplication. Here's the quick sort code. So pretty conventional quick sort code. I have swap, right? And I have this is the quick sort code, and this is the Platonic sort code. As you can see, I indeed implemented that, right? And now, okay, so this is the inner part of the Platonic sort. So, okay, I already run it, right? So if you don't trust me, I can run it again. Oh, it's even faster now, right? So this Platonic sort for the same set of data size, it takes less than 1 second to finish it. And for quick sort, well, it's supposed to be really quick, right? According to our understanding about computer. But because the limitation of GPU architecture and also because of the limited parallelism of quick sort, it actually runs really slow, right? I'm trying sometimes, oh, right? So it takes about 22 seconds to finish the quick sort. And both of them are running on top of an NVIDIA GPU. And you might think about, like, I'm using a grandfather old GPU, but it's actually a GPU under the A.Loveless architecture. So it's the latest GPU that you can ever buy, right? So even with the latest GPU, you can see this significant difference, even though quicksort has lower complexity. But on GPU, it's not as performing as another algorithm with higher complexity. And GPU is well known for its thousands of ALUs. So it has a lot of parallelism. You can consider it's close to unlimited parallelism. And you can even imagine if we have unlimited parallelism, the difference between Platonic sort and quick sort is going to be more and more significant. And why this is that case, we will talk about this later in the quarter if you're interested. But I just want to put a seed in your mind saying that, okay, why do I need to stay in this class instead of just shopping around? Okay, so again, program performance scale is then algorithm complexity. I also remember a lot of people went back to their seats with this. So let's go back to this matrix multiplication, right? So this matrix multiplication, what's the computational complexity of it? N cubical, right? So can I do this assumption? So if I have a matrix that size as 1K, it takes about 2 seconds. Can you tell me if I make it 2K, how much time is it going to take? If it's uncubical. 16, right? 2 times n, right? Okay, so let's run it. I have demos, right? So this is a class without cheating. I'm not like those theorists. They use mathematics to cheat you. All right. So, okay, so I run this program, right? So it's 124 indeed, 2 seconds, right? Did you guys see that? Now, 2K. How much time? So 2 seconds, we said it should be 16, right? So sometimes I really feel those people doing talk shows, they are really talented because at this moment of time, they must have some joke that they can tell people. But right now, I'm thinking, what kind of joke can I talk about? And I think it's more than 16 seconds, right? So you see this, it's close to 24 seconds. So it's far away from 16 seconds, right? So what does that mean? And I already exclude the time of warm up the code of initialization, right? So it tells you one thing, right? Computational complexity is junk. I should take this back. All right. And the reason why is because, as you might imagine, matrix multiplication needs a lot of space. Memories, they are in this slow. So that's one of the reasons why the computational complexity doesn't work out. And the main reason is because a lot of the theorists, they would assume every operation is weighted equivalently in computation. But in fact, that's never true. That's never true, right? So that's why those theory algorithm class, what they told you, actually failed. And if you try to use your data structure book to implement your program, I'm sure that if it's a company that really cares about money, cost, performance, you will be fired. Right? So a lot of my friends, they work for game companies, they say, well, you know, the best data structure that we use most of the time is array. Right? And that also explains why sometimes your game crashes, because array out of bug. But the reason why they use array is just because it's faster than other data structures. Right? Okay, so in volume architecture, we have been talking about program performance. You can pretty much imagine, okay, it's the processor dominating the execution of your program. So the processor is the main force how we improve the performance of our programs. But if we look at the curve, which I draw from 2014 to 2022, we only improved the CPU performance by 3 times over the last 8 years. And so definitely there is not sufficient, and there are some challenges in von Neumann architectures. So the first thing that one of the very early questions we asked about is Moore's law. So a lot of you got this wrong, but can some of you at least tell me what is Moore's law about? From your knowledge, from the best of your knowledge, from the day one, I think this is something like a CS203.
The number of transistors doubles every 18 months.
Okay, the number of transistors doubles every 18 months to 20. So actually, yeah, 12 to 24 months, on average 18 months, right? So that's the original definition of Moore's law. So conventionally, we say Moore's law is the driving force of CPU performance gain. And it's actually coming from the paper written by Gordon Moore in 1965. And Gordon Moore is also one of the co-founders of Intel. And If you don't have time to read the paper, let me give you a quick glance of the paper. So first of all, the first paragraph, so a lot of YouTubers and TikTok does this, right? 20 seconds of a Moore's Law paper, right? So let's try to see if we can do this in 10 seconds, right? It's more like a TikTok, right? So first, ICs, integrated circuits, they are more increasingly popular. They are well established, so you can trust them, and they are more reliable nowadays, and they are really small, right? And it's easy to manufacture, and we are going to make it smaller and smaller, and heat is a solvable issue, and design IC can be really easy, and a lot of you who took very low class, you think it's bullshit. I understand that, right? But this is the whole thing about Moore's Law. Did I finish it in 10 seconds? Is it good enough for TikTok? Maybe, okay, right? Oh, ICs are widely applicable, right? But a lot of you was thinking about, okay, our processors are not getting faster anymore. It's because Moore's Law is continuing and slowing. So, sometimes being a scientist or an engineer, you want to say things based on truths. So, here's the truth I got. So I grabbed the plot from the transistor counts from Wikipedia. And these are public data. You can definitely pull it down. The vertical axis is the density of the chip by millimeter squares. And it's a log scale. And the horizontal axis is the number of years. And we are in 2023. And I also have the data of 2023. I just updated last month. So it's very up to date. And typically, you say it scales well on log scale graph if it's a straight line, right? So let me draw a straight line from the very beginning of 1970 to 2023 for now. Is it a straight line? Is it a straight line? Mostly. So, did you see any slowing down on Moore's Law? No. Not at all. Right? Like, why your iPhone 15 Pro, is it 15? No. Oh, okay. Like, I have an iPhone 15 Pro. I'm hesitant to have it right now because I heard it's really hot, right? But why is it really hot? Because we are using a 3 nanometer, right? So TSMC, Intel, they are able to shrink more transistors within the same area still. And the rate of how they can make your transistor smaller is still the same at the time Golden Moore wrote the paper. Is Moore's Law dying? Golden Moore has died, but Moore's Law is still alive. Right? If you don't believe me, at least believe this chart. Right? The data tells you Moore's Law is alive. But why can we not make the chip even faster, right? So the reason is, so I just copy paste the same line here, right? So supposedly, right, if Moore's Law looks like this, our processor should grow like this. But the thing is that we have the power density issue, and I kind of like revealed that, right? Why iPhone 15 Pro is really hot? Because we are not able to address the power issue of more advanced process technology. So, long time ago when I was a kid, we were trying to use processor to cook an egg, and we did get very big success, and the egg is really, delicious. But and after 21st century, we are hesitant to do that because your egg will actually get burned, right? So, because at the time, the power density of your processor is actually the same degree as a nuclear power plant. And if you don't control the power, the density of your chip will be the power density of your chip will be as hot as some surface. And we definitely don't want this to happen. So the only thing we can do is to slow down our processors so that we can still maintain the same power density or at least make the heat controllable, right? So what turns out is this.
So the first thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
So if you don't know who they are, the left-hand side person is John Hennessy, and the right-hand side person is David Patterson. And this is so probably because of Jeffrey Hinton mentioned that, the biggest success of DNN is after we made the computer faster. So right after the year of Jeffrey Hinton got the Turing Award, these two guys, they got the Turing Award. And those are the two guys who wrote the textbook. And that's it, right? So what he just said is that, in the past 30, 50 years, computer architects as the hidden figures, we try to make the computer as fast as possible. However, the era has over. Even more slow continues. We are not able to make single thread performance even faster. So where's the future?
The future is parallel. Single cores are not getting any faster.
All right, so then what does that say is that instead of seeking performance from a single processor, we try to build multi-core processors. However, even multi-core processor has its own limitations, so that's why a lot of people nowadays are seeking performance from this GPU architecture, by which we added GPU into the computer system. And however, if you look at the GPU performance, sometimes I hate people from I hate the CEO of NVIDIA because he keeps lying to people. So they give you an impression that GPU is actually meeting the demand of modern software. And the answer is definitely not right. So again, as a scientist, as an engineer, everything needs to be based on real data. So the green bar here, the green line here is the GPU performance. So again, well, CPU is not doing so well. We only improved 3 times the performance over the last 8 years. And for GPU, it's only 8.5 times. But if you look at the red line, so the red line is the data that I gather from a lot of published papers, and I try to count. If I want to finish training a model within a week, then what's the flux, floating point operations per second that I need to finish training a useful model? So the red line is like that. So indeed, in 2014, GPU is actually good enough for CNN. However, it's never true after 2016. So and like even AlphaZero in 2017 is already way larger demand than what the GPU can support. And there is a new law, right? People like new law. So Moore's law saying that the transistor can double every 2 years, and what new law saying that the demand of AI ML models doubles every 3 to 4 years. And in fact, in the past 8 years, here is the amount of demand increase. So it's a lot more than a GPU. So when people talk about ChatGPT or these large language models, we have trouble of running them as a small company because think about this difference. The difference here is the amount of GPUs that you need to train a model efficiently and to make your service runnable. That's not possible for small companies, small startups. So sometimes I feel LLM is potentially killing all the innovations of computer science because it prevents small companies, small startups to put their innovative idea into practice, unless you team with a big company. So again, GPU is not enough. So we start to have FPGAs and TPUs, which is a tensor processing unit invented at Google. And tensor processing unit has been intensively put into production nowadays. And if you are running any Google service, including BART, that will be using TPU. So with that kind of spatialized unit, we can better tackle the demand of AI ML applications. But again, given it's growing so fast, right, it's very difficult for simply the effort from the hardware to make it happen. So definitely, as a software engineer, we need you, right? And also, conventional problem, processor memory gap. And it's going to be more and more significant in the era of heterogeneous computing. Because think about this, because everyone is not in processor. And the only way we can synchronize, communicate is through the memory. However, remember the gap is really slow, right? So a lot of data movement, a lot of latency being wasted because of the data exchange. So that's why we want to be in a class. And now, as the first class, there are always questions like this you are interested about. What's going to be in the class? So again, we are now in a world of heterogeneous computer architecture in addition to conventional volume architecture. So the course will have 4 different parts, 4 different main topics. The first part is how we evaluate the performance fairly. And the second part is how the computer system bridging the gap between processor speed and memory. And as a programmer, how can I optimize my software to be more efficient? And again, processor itself try to exploit as many parallelism as much parallelism as possible. How can I coding my program in a way make it more efficient? And again, we are now in a world of parallelism. How can I make my code more efficient in the era of parallelism? So a lot of you might come here and imagine this is a very hardware-oriented class, but I want to tell you that's not true. This is indeed the only class in the CS department will tell you how to write your program more efficiently. And here's a tentative schedule, and we have a lot of paper and assigned readings, and they will cover performance, memory, processor, and parallelism. And logistics, what you're interested about. So first of all, who am I? I am an associate professor at UC Riverside, and here's my website. And if you want to communicate with me through email, I'm suggesting you to put this as the email for CS203 related stuff, because sometimes it's just emailing me or the TA. We are not synchronized, so we might give you a different answer for that, right? And you don't want that. And also, this would make sure that someone, either me or the TA, will see it, right? So, and another thing is that the fundamental reason is the campus ID is really problematic. Is that they created another account which sounds like me, but actually not me. So a lot of people send to that account. A lot of email doesn't go to me. So if you try to send through the campus email, there is a very high probability that I won't receive it. So use this email address. And as I mentioned earlier this year, I was spending time at Google as a visiting scholar, and the reason is because a lot of my research is highly related to Google's tensor processing unit, and that's why I'm working at I was working at Google's TensorFlow team, and I know a lot of stuff, what they are doing, and what's interesting, and I was lucky that I was at the epicenter of the generative AI revolution. So I can definitely tell you a lot of things, right? So although not in a degree that I will leak you to any Google secret. For myself, I got my PhD in UC San Diego, and my research interests, I'm doing general purpose computing on AI, ML, and NN accelerators. That's why Google want me. And in the past, I've been doing a lot of data storage research and everything else that sounds fun. And fun fact about me, I was once considering a career path as a singer, but went back to academia because I was unsuccessful, right? And here's our TA, Kimball. Do you have anything to share? Fun fact, he knows how to solve Rubik's Cube. Do you bring one with you today? No, okay, so we cannot prove it. Again, if you want to contact him or me, this is the address. All right, and he has office hour on Monday or at 3 p.m. to 5 p.m. And here's the course website, which contains every information that you need for the course. And for this class, I am not a big fan of using Campus and eLearn, or say eLearn, because I had enough of it. So I'm deciding to retire it. Everything is based on the course website, and here's the location. And on the course website, you will be able to find a calendar as well as our schedule and download our slides. And I also create a small app allow you to look up your grades on the website. So if you go to our website, that's pretty much what it looks like. And as you can see, we have different sections. I will put the TA information later because I just got him yesterday. The original TA, he got the offer, but he declined because he heard it's computer architecture, so he declined it. And that's the truth. He thinks it's too difficult, right? So you must be prepared. And here we have the Grayscope link, we have the Piazza link, we have the YouTube channel, right? So that's why I need to be loyal to my contributor. And here's a Google Calendar. You should subscribe it because it actually tells you all the important deadlines and when you can find us as an office hour and also the location. So this is highly recommended. And you can see the course overview, the grade policy. I think a lot of you already signed a course agreement, so you must be familiar with the website already. And it will show you all the deadlines and for you to track things down. And there is also a little section here that you can look up your grades. Because Google Authentication doesn't allow pop-up inside the iFriends, so I won't be able. So even though it says you have to log in here, but actually you have to log in through here first and see your grade here. All right. So here's the summary. So we have a lot of course resource. Finally, I'm glad that we get rid of eLearn. But most of the stuff you can find a link on the website. So website is indeed the most important thing that you should always keep track of. And for every lecture video, I will try my best to put all of them on the GitHub. Sorry, not the videos, on the YouTube video. So YouTube channel. So you're highly recommended to subscribe. You shouldn't donate to me because it's academic, right? And I should not charge you for that. Plus, you already donated a lot to UC system, right? So don't do it, right? And office hour locations on the Google Calendar. Finally, learning experience. So we are back in person, and as you already experienced, this class may be a little different from what you ever experienced, right? So most of the lectures, as I could imagine, is pretty much like this. So like Irving Burnett, Anderson Cooper, right, or Oprah, right? So most of the time, right, you just sit and watch, right? So I don't like that kind of stuff. So what I like is just like what we experienced. I like to have a game show, right? So I hope we have some stages here and it's too crowded, so some of you cannot even get up there, right? Something like that, right? So I expect the lecture can be somewhat a game, right? So one of the main way we are going to have the game is through a teaching method called peer instruction. So the idea of peer instruction is that we are going to have some pop-up questions during the lecture, and for each pop-up question, you are required to stick individually first and then vote on your answers. And by looking at your response, I will decide if we need to have group discussion or whole classroom discussion, right? And the thing is that you don't want to participate in a game like Ninja Warrior without any preparation, right? So to prepare you for that, we require to do some reading quiz, unfortunately. But the process of the class will require you to read, think, and discuss. And before the lecture, you are going to have reading quizzes that's based on the assigned reading or the textbook. And it's going to be on Grayscope. And actually, there's one up already. And there's no time limitation until the deadline. Because the only purpose that I wanted to go through with the reading quiz is to go through the material at least. Right? So there's no time limitation. You are more than welcome to open up the quiz without submitting it. You can look up the answer for second 02 the deadline. I'm okay with that. But the only thing that I'm not okay with, because the whole purpose of the reading quiz is to prepare you for the lecture. So there's no makeup for that. And for peer instruction, I know we have a lot of things in our life, and sometimes I feel sick, I feel sleepy, right? For me, I'm unfortunately being a professor, so I cannot have an excuse of not being here, but you could because you are a student, right? So I appreciate that. I like to do that when I were a student, so you are allowed to be not around for 50% of the time, but still get full credits for the participation. And you can even, and the participation is counted as an assignment. So we will drop your lowest assignment, so even though you don't show up for the whole quarter, it's still fine as long as you're turning in all the assignments. And we use an app called Poll Everywhere. And download the Poll Everywhere and and log in through the app using your UCR account. That's the peer instruction experience. And the second part of the experience, as you already see, is that we are going to use Jupyter Notebook for our assignments. So every assignment is going to be done through Jupyter Notebook. And it's a popular interface for machine learning, and even Google, they have the Colab as the copycat of Jupyter Lab. And I also set up the service in the school to provide you this. So each assignment will be pretty much like this website. Hello? Why am I? Okay, so this is an assignment, right? So as you can see, an assignment will contain several sections that you should definitely read through. And within this Jupyter notebook, you are allowed to execute programs like this and compile code like this. Oops, where's and draw figures. Oh, sorry, I should start here. You can also draw figures, and we would definitely ask you to draw a few tables and figures, right? So when you take this course, you will also be a very good data analyst as a side product of taking this course. So this course is definitely something giving you more than just computer architecture. And we also provide tools for you to compile to see how the program is structured. So it's definitely interesting. Without Jupyter Notebook, there's no way conventional architecture class can make it happen. So you can imagine how Jupyter Notebook would make your assignment very different. But it also means that I really have to do something for each assignment. Copy paste is not going to work, right? So we have a video. It's a 7-minute long video that I strongly encourage to watch first. We'll teach you how to start working on our assignment. And indeed, the assignment 1 is going to be up a few minutes later. And in addition to Jupyter Notebook, you are also going to be familiar with the skill using GitHub and Git. And in each assignment, we have 3 types of questions, and they have a lot of questions, so start working on earlier. And you are going to submit your assignment. Also, we have pre-programming assignments through GitHub, through Grayscope. We still have, unfortunately, midterm and finals because there are conceptual questions that are hard to see from the Jupyter Notebook. And here's the schedule. And for the final, we have 2 parts. The first part is in person. It will be the last lecture. And if you are taking the MSCS comprehensive exam, that's the time we are going to have a question. And for the second part will be online because I like to test how good you are being a researcher. So the second part will be online open book. And here's the course grading breakdown. There's a table here. You can find the same table on the website. And don't cheat, and sometimes, so this slides, I think you can go through. And let me see. Okay, so, well, you must go through this course agreement, but I believe I probably see more people than the ones who submitted the course agreement, so I bet some of you probably add this course at the last minute. So if you haven't submitted the course agreement, first of all, you won't be able to access the Data Hub service that allow you to start working on the assignment. So you have to do this as soon as possible, and if you edit late, send us an email saying that, okay, I have to edit late because I have to send this late because I'm edited late, right? But the whole purpose is that send us an email so we can set up the account for you. All right. So one habit I like is because I've been teaching for more than 10 years, and I like to take a photo after the end of the quarter, right? A lot of them are still smiling, right? So it looks like the class is probably okay. And I've been teaching at 3 different schools, and during the pandemic, I feel like I'm teaching for the school called UC Zoom, right? And then we are now back in person, and this year I hope I can have your picture here. All right, questions? All right. If not, before I leave the classroom, several things that I need to let you know. So first of all, check our website, log into the Grayscope. There's a reading quiz due next Tuesday, before the lecture. And assignment 1 due next Thursday. And log into Piazza if you need to discuss with us. Other than that, I will see you next Tuesday. Enjoy the rest of your week.
You can take me anywhere. You're making me feel I'm loved by somebody. I can give